Okay, so these dots are just unbelievably, staggeringly bright and powerful, but still look like dots. What's going on here?
Well, I think we're going to need some clues, Paul. So let's look at how bright they are over time, because one could imagine if they just start and disappear, well, that wouldn't be very interesting. But this is a graph of how bright they are over time, over thousands of days. And you can see they're not constant in brightness. And I guess that's not too surprising over thousands of days. But what's really interesting is they're changing by a factor of 2 in brightness over periods of just a few days. Now that seems to me to be an interesting clue.
I mean, imagine these things are brighter than galaxies. So let's imagine they were bigger than a galaxy. Galaxies, say, 30,000 light years big. Let's say every star in a galaxy decided to double in brightness instantaneously. I don't know how, maybe they've mass suicide pact or something. Would we see a doubling in brightness like this? No, we wouldn't, because the stars on the near side of the galaxy are 30,000 light years closer than the stars on the far side. So we'll see the light from the near ones getting brighter 30,000 years before the ones at the end. So basically, a galaxy, or anything that big, cannot change in brightness in less than timescales of tens of thousands of years. If this thing is changing on timescales of days, it can't be bigger than light days across.
But light days across is the size of our solar system. And it takes about a little less than a day for light to get out to Pluto. So we need something that's insanely bright, the size of the solar system.
As bright as your 10,000 galaxies and smaller than our solar system. This is looking pretty weird. Well, here's another clue.
Right, so this is a picture taken in radio. Now you remember that when these objects were first looked at in optical, there was a little squiggly thing next to it. Well, this is what a really good picture with a modern radio telescope looks like. And what we see here is apparently jets shooting out from the source. And what's really interesting is if we look at these blobs and trace them over time, especially the ones right up close, they appear to be moving faster than the speed of light. Now, we can understand that it's not faster than the speed of light. If we do the calculations and figure out what their motions are, using the effects of relativity, we realize that they're traveling almost at the speed of light.
And the really crucial clue here, first, they're squirting stuff out at close to the speed of light, but secondly, these jets are millions of light years long very often. What that means is, we know these things stay bright since the 1960s when they're first observed, but in fact they must have stayed bright and powerful for millions of years. You can't squirt out a million light year long jet unless you've been in action for a million years.
So these aren't just things that are, fly by the night. They really have to be there for a long, long time.
So they're incredibly powerful, but they're not like supernovae or gamma ray bursts, which are flash in the pan, incredibly bright but don't last very long. These things put out comparable amounts of power and keep doing it for millions of years. So here are our clues. Luminosities of more than 10 to the 40 watts, just staggering amounts of power. Sizes of light days or less, so incredibly small, and can stay active for millions of years. So what could possibly cause these?
Well, we're going to need a lot of energy, that's pretty clear. So let's think of our energy sources. Now there are 2 ways to get lots of energy out in the universe. One is the way our sun does it, nuclear fusion. And the other way, the way our sun got started, is energy from gravity. So Paul, why don't you have a little look at those 2 sources?
Okay.